Numerical integration is a very important process in structural dynamics. Many times we can't use the previously developed analytical tools because the loading or the boundary conditions are given in a pattern that makes an irregular response called a transient response. Sometimes the best way to solve that problem is through a time stepping and a numerical integration of the equations of motion of the system. Fluid systems often are governed by first-order differential equations or are at least simplified to that form by change of variable. Structural dynamics problems, however, are usually studied with second-order differential equations. I'm going to approach the entire technical topic by giving two lectures. The first will be on integration of first-order equations, and that is relevant to fluid mechanics, flight mechanics, and some other disciplines, and is very good for looking at stability of the system of equations and the numerical process. We'll follow with a second lecture on integration of second-order differential equations. That's the one that's so popular in structures and primarily the Newmark beta method. So I think I want you to bear with me on this first lecture on numerical integration of first-order differential equations. It's kind of fun material. It will help you talk with your counterparts in fluid mechanics, and it helps us understand stability concepts. I mentioned some of the ideas about indefinite integration. I'll show some examples of indefinite integration that are more simple, namely the trapezoidal rule and the Simpson's rule. And then we'll progress to a more complicated law, Hammings' general approach, that lets you handle many different integration schemes simultaneously. Then we move on to a differential equation, which is a little more general than just numerical integration, and I'll follow with some problems in a problem session. Let me show you a table of different physical problems that we're interested in. We'll concentrate on forced vibration in contrast to some of the free vibration we studied earlier in the eigen problem. So here we're not so interested in finding normal modes, but rather looking at a forced response problem. Even then we branch into transient problems and steady state problems. We've already had a bit of a look at the steady state problems, particularly those that are harmonic, through our frequency response approach. But we're really interested in transient problems here, and these arise because initial conditions can cause a system to move in an erratic manner, or you might have impulsive loads, or you might have a load system that in some piecewise sense is easy to handle, but when you add varying kinds of such loads in some random way, such as an automobile that moves from a rough road onto hitting a curb, up on the sidewalk and running over a bunch of blocks and so on, crazy driver, you get into these cases where the loading pattern is so non-analytical that you can't really handle it by analytical methods. You can either study these transient problems up here by directly integration in physical variables or by integrating using modal methods. I've already discussed that we can attack the first order equation, which is the topic of this lecture, or attack the second order equation. The modal methods actually are sort of a last minute add-on thought here, and they're relatively easy to understand once you have figured out how to do the integration in physical variables. Let's now discuss indefinite integration and compare it with the definite integration that we previously used in static finite element methods. Previously, we had an integral of a function that was known over a given domain, say from A to B. this integration gives you a number, and it's basically the area under a curve. We found an alternate numerical way to integrate by using certain sample points, or abscissa, and then using weights that emphasize those functional samples at those sample points. And this was called Gauss integration. It was a powerful method and was quite accurate. In fact, gave, roughly speaking, twice the accuracy that you got out of other sample points that might have been proposed, which were evenly spaced in this location. But now we want to do something different. Now we want to get something like this, where we integrate a system from some starting point with starting conditions here, from A to a current time, let's say. And this time we're not asking for a single number, like a single area under a curve, but rather a table of numbers. And this is sometimes called an initial value problem, whereas what we had done earlier had to do with boundary value problems. The new thing that occurs that is scary is that you can get numerical instabilities due to feedback in this type of indefinite integration. The reason is that there is some accumulation of error as you move from the present time to future times, and if you carry that error forward, sometimes it will make your problem move away from the desired answer. Furthermore, sometimes it will erratically diverge, or it will oscillate about that desired solution. So these numerical questions of accuracy and stability are really important for us. Let me now give some examples of numerical integration to build some intuition. We'll show you the simple trapezoidal rule and Simpson's rule. This will let us develop the terminology as well. First of all, this problem could be posed in a differential form as shown here. You might have the derivative of a function given over an entire range of interest of time, and then you might have, for instance, for ease of solution, a zero starting condition. So this would be a body that would be starting at a point 0. Physically, this corresponds to a dashpot under a load that's given as a function of time. I might sketch that up here just to help us remember what we're doing here. See how good an artist I am today. You can also pose the problem in an integral form, which is completely equivalent to the differential form above. Here, the fact that you have started at some time A is represented in the lower limit on the integral, and the fact that you want this process to continue to an arbitrary time is shown in the upper limit and carried as the free variable on the left. I've shown a dummy integral variable here of t tilde in 2 places. Unfortunately, it's common in the literature to drop that tilde, leaving this as the standard expression. I'll do that as well, although I do it sort of hesitatingly because I'm kind of a purist and I prefer the form up here. But I think once you've been told, you understand that there's a difference between these dummy variables inside the integral and these free variables that remain of interest to the engineer scientist. This looks a little more like the fundamental theorem of calculus if you use the velocity here rather than the symbol f. And of course that's what this bottom expression really is. Let's look at a very simple form of numerical integration called the trapezoidal integration rule. And I like to show figures for both the function and its derivative because it helps you understand that the solid line below is a curve that is known for typically all time, and that might be the force applied to the dashpot, for instance. Then the curve up above represents the position of the dash pot, and it's known for past times up through the solution which you have just finished, but is not known for the next time step. These time steps on the horizontal axis are presumed to be equal intervals here, some sort of a delta time interval. Now, we will concentrate in the trapezoidal integration on 4 different sample points here. The function at the, let's call it the past time and the present time, and then the derivative at the past time and the present time. And those 4 sample points are all given in red, with the star being the unknown one. The idea is to relate this starred quantity, which is what you're trying to find, to the other 3 quantities. Now that's done in a fairly straightforward way here by saying that this star ought to have the same value as the past value, plus it ought to have some measure of the gain in elevation here due to the slope at this past point, or even the slope at the current point, which would help you because it would be a little more accurate. Or you could take an average of those 2 slopes, as is done here. So the actual trapezoidal rule then says, let's take the new value as the old value plus the average slope over the time step, and then multiplied times the time step, which here I'm calling h. This is a very stable way to integrate. It's a very brute force approach and has been used a lot historically. A minor modification of the trapezoidal rule would be the midpoint rule integration, and that's where you try to improve your estimate of the slope. We still will predict the starred quantity, which is here, by its previous value, which is here, plus a representation of the slope in the time step taken at the middle of this region. So that means a new kind of a sample at a half time step shown here. This has got to be related to the some of the middle point theorems out of advanced calculus. There's several of those Rolle's theorem and the midpoint theorem that say that in the interior of the region you have the best estimate of the slope of the region somewhere in there, and here we take the half point. Let me also comment about Simpson's rule. I'm going to do Simpson's rule more thoroughly in a problem in the problem set at the end of the lecture, because it is a little more complicated. It's not quite as easy to say, but in Simpson's rule you find the value at this starred quantity by using the previous value 2 steps earlier, and then the slopes at these 3 large circles I'm drawing here. So you'll see how that's done later, and we look at the stability of that. But Simpson's rule is basically using a parabola to pass through 3 points rather than a straight line through 2 points in the trapezoidal rule. Hamming has proposed in his book a method for generalizing the concept of numerical integration and giving one approach that has a number of coefficients in it and which reduces to many of the great integrating formula. So we'll take his approach because it really has a unifying effect on this topic. Hammings says that when you're interested in doing this indefinite integral, and if you know the quantity below, which is the derivative for all time, then you can find this starred point by, in general, getting information from 4 previous functional values and from the current velocity and the previous 4 velocities. Again, the analogy of the dash pod is appropriate for us, so you can always think in those terms. Now, by how you choose these samples and how much you weight each one of those, you then can get most of the good integration formulas that have been developed through history. And the names I've heard over the years and always been just awed by these curious integrating formulas, and yet they all fit into this common approach of Hammings. We'll start off with the approach of using 3 earlier samples of the function and the current and 3 earlier samples of the derivative. This means there are 7 sample points used. There were a couple more there in that last figure that we'll pick up later for what is sometimes called the predictor-corrector method. But for now, let's look at this general expression then. Here is the value that we're trying to find at the n plus first time step, and that corresponds to the star that I've been showing you. And then here is a sample of the function at the previous time step, 2 previous, and 3 previous time steps, with a coefficient A0, A1, A2 entering, and these are to be set by the specific processes. Then on the slope term, we have the multiplier h, really reminiscent of the trapezoidal rule, plus the current value of the derivative, the past, and then the preceding 2 terms. So all told, there are 7 constant a's and b's here. This final term is an error estimate that comes from the Taylor series with remainder, and this shows that you have an error after you've done this integration that varies as the 5th derivative of the function evaluated somewhere at some point theta in the time interval of question, the one that you're currently stepping in. The factorial in the denominator is a thing that helps out on accuracy, and this is a rather accurate formula here. The theta is not known precisely, but is a way of bounding the error in your problem. So I mentioned at the bottom here the derivative evaluated at this sample point somewhere in the time step. In this rather general version of Hammings' integration formula, there are 7 constants to be determined. In indefinite integration, we have to worry about 2 things. We have to worry about accuracy and stability. Hamming chooses to use 5 of these parameters for accuracy and 2 for stability. And that, as we've mentioned, encompasses a lot of the earlier numerical integration schemes. The way that we can make Hammings' formula accurate is to demand that this integrating system work exactly for certain trial functions. For instance, if we tried to integrate a constant 1, we would hope that the answer would stay at that point and not move. If we have the answer that the displacement of a dash pot in our example first order integration would vary like time, we would like that to be exactly integrated. You proceed up this polynomial chain and use the accuracy at each level then to improve the process. If we do these 5, then we can see that we can exactly integrate a function that varies as high as a quartic in time dependence. This integration is a linear process, and so the accuracy of the components here immediately fit into the accuracy of the total. Now we still have two parameters left to be set for stability, and that is quite a task. We're going to spend some time on that. The condition that you exactly integrate these polynomials is called a defining equation, and we will have 5 defining equations as a result. Let me work out the first defining equation, but I'll just state the results of the remaining 4 so we don't bore you to death with algebraic computations. Here's the situation we would like to exactly integrate. And by that I mean that there's a horizontal line here prior to any sampling where the velocity field is 0, and we know that this function is here, that the displacement is always 1. Now what have we done? We really have taken a dash pot, pulled it out to 1 unit of displacement, and then we put 0 force on it. And so hopefully it's going to stay there. Now I know that that sounds kind of stupid to ask such a simple task, but some of these methods would fail if you didn't impose this. It's a little bit like telling an unruly kid to sit still in the chair, and if the kid's stable he will, but he or she will, but if they aren't then they jump all around and bounce around the kitchen. So the indefinite integration that we have here, we're going to replace with a numerical version. And we know that on the left we want unity, and then on the right we know that we're going to sample these circled quantities here that have the A's on them, and these circled quantities which lie on the x-axis which have B's as coefficients. Well, literally this is a time axis, I shouldn't call it an x-axis. And I write that expression below here. Hopefully the error will be 0, so we'll put a 0 in for error. Now our job is to evaluate these relations. First of all, the zeros for the samples on slope have knocked out all of these terms, so those disappear. In this expression then we're only left with 1 equals A0 plus A1 plus A2, and that is our defining equation. So I'll repeat that defining equation and use it to solve for A0 in terms of the other A coefficients. And it's here. Now, if you do the other 4 defining equations, they uncouple in a nice way that leave A1 and A2 as independent coefficients, but then put conditions on these others. And we're able to determine this estimate of error also. That would take some outside reasoning in order to get this estimate for E5. The way to think about Hammings' formula as we've progressed with it is to think of it as a formula that has 2 variables in it, or 2 parameters, A1 and A2. They haven't been set yet, and they're going to be used for stability purposes. But consider that the other parameters, the B's, are already chosen for accuracy. One thing we can do then is to plot the accuracy, or that error term, as a function of A1 and A2. And that's done in this figure. Here we have A1 on the horizontal axis, A2 on the vertical. I set some boundaries here by understanding what goes on later, that there's some limit to how far we have to look at these variables, and there's not much need to consider A1 and A2 beyond those boundaries. Interesting things happen all within this rectangle. The error tends to become less and less as you choose A1 and A2 down in this corner. In fact, although this figure doesn't have the 0, there would be 0 error if you pick this point in the bottom corner. It turns out that that golden point for accuracy is overwhelmed by instability problems, and we never really use that point, so that we're forced rather to accept a modest amount of integration error in order to get stability. We can't see that yet. We need to develop some stability arguments, which I'll now do. Stability is a very interesting topic, and stability of this integration process is, I think, one of the most fascinating things in this course. It's kind of academic, so you don't have to get off on it like I do so much, I guess. One of the ways to think about stability is to say that if you give a small perturbation to a system, then the response ought to be small as well. I think this has a street interpretation in terms of personalities that are unstable. If you have a person sitting in your attic in a rocking chair and you come up and you just touch them lightly on the wrist and they explode and bounce off the ceiling and walls, you'd say that person's not stable. But if you actually punched a person or did something really strongly disturbing and you got a strong reaction, that wouldn't be too unusual. So the idea is in stability to provide a small input and see if you get an unreasonable output. We're going to do that here by specifying a system that's at rest basically for all times. It has no velocity at any time shown in the bottom curve, and generally speaking it has no displacement up to a present time where suddenly you just give it a small touch and you just make it jump up an amount epsilon here. Now, what could the system do at that point? We might theorize that it could return back to the undeformed position. It could stay where it is, or it could oscillate and grow bigger and bigger, or it could diverge in a monotonic way. Now, those four different kinds of behavior in principle are possible. For our particular problem of a dashpot with a force, so we really don't have the physics that would bring back the disturbed point back to zero again. So I don't think you should expect that. It could happen, but it would be a rather lucky numerical method that would do that. It could just stay where it is or do some really tiny oscillations about that disturbed position, and that you would consider stable. A diverging oscillation would be unstable, and a growing divergence like this would be unstable. So there's all sorts of behavior, and we're going to look at this now. We'll take some examples. It's kind of a fun process. You probably remember the rectangular figure where Hamming is able to describe a number of processes lying within that rectangle which have varying accuracy and varying stability. If we take the general formula of Hemmings and then apply it to our current case of a system at rest but with a small perturbation, the zero velocity knocks out all the B terms, and we're left with these other terms. Remember that the term A0 had been previously found in terms of A1 and A2. And so this is a general integrating formula with the coefficients yet to be chosen. Let's suppose we pick a specific integrating formula. A1 is -1 and A2 is 0. Now in that rectangle that would lie to the left of the origin. I guess if this was the origin it would be over here somewhere. And now we're going to check and see, is that stable or not? So the formula becomes, when you put these coefficients into this general formula up here, you will find after just looking at the way the terms combine that this is your integrating formula. And we can give a name for this. This could be the Smedley integrating formula. We don't know if it's worth a darn yet, frankly, and we better check it. See if old Smedley knew what he was doing when he came up with this formula. You can develop a little table like this where you increment time and you march forward in time as shown, column by column. And then we know that there's no force on the system for all time, and that's the lower row of zeros. But we know that we're going to bump up the displacement u at the present time 0 to a value epsilon, and then we don't know how the system's going to respond after that. But we do have an integrating formula that we can apply now, and it uses the present values and past values and then tries to predict forward. If we're trying to find the component u1, then the formula gave us the rule of taking 2 times u0 and then minus u at the previous time. When we put those numbers in, we realize that our little bump, our little perturbation epsilon, does cause a change in the predicted value for u1. In fact, it doubles it. Since the system was at rest earlier, that didn't have any effect, bringing a 0 in. Now we've filled in one more entry in our table. You could go back on your notebook and do that now and put 2 epsilon in there instead of the question mark. You repeat the process and increment your time forward so that now it's u2 that's unknown, but now we know u1, in fact it's 2 epsilon. And then the u0 that occurs here is still the epsilon value that we caused it to be. So you get an epsilon here and a 2 epsilon here. 4 epsilon minus epsilon is 3 epsilon. And I think this ought to be looking ominous already to you. When you do one more increment, you get that the previous value enters here, the 3 epsilon. You subtract off the value before that, and you end up with 4 epsilon. So what is happening? Well, I'm afraid Smedley's rule was not a very good integrating formula. So this solution is really starting to diverge. In fact, it's moving away on a straight line away from the original rest position. Now true, we bumped it a little. We came in and just slightly touched it, but boy, it just takes off after that. And remember, it's doing that under no external force field. In other words, nobody's making it do that. And there is a damper involved. So, you know, this is doing it, I suppose the physics is a little hard to discuss here. This is purely a numerically induced instability. There's no way for this to happen physically because it should damp out physically. So, poor old Smedley, I guess he probably had to end his career as a ditch digger instead of a great mathematician. Now, let's pick another formula and let's take these coefficients chosen for stability to both be unity. And that would be in the upper right-hand corner of Hemmings' rectangular diagram. And so up in here somewhere. And when you work that out with a tabular approach as we just did, we find that that one, upon perturbing it, comes back with a vengeance in the other direction, and the other, and the other, and diverges in an oscillatory way. And so that formula is no good either. I think you can see now that this question of stability is really crucial for integrating these first-order systems. One can map out the boundary of a stable region for this numerical integration by trying different values of the A1 and A2. And when you finish, you come up with a region shown in this figure. Here we see that when you lie outside the interior region, in this crosshatched region, you become unstable. Now the instability can be neutral right on the boundary. It can be an oscillation that doesn't grow in size, but as soon as you get outside that boundary, out into the crosshatched area, you really do have an instability. And so you wouldn't use methods at all that lie outside in the crosshatched region. We don't track this little corner up here. It's so far out we don't care about it. But this is all unstable around the edge. Another concept dealing with stability is response to noise, and I don't understand this fully, and it takes up several chapters in Hammings' book, and it would divert us from our normal structural analysis, I think. It's a big problem in electronic communication where you get static in the voltages that occur in the system, and that could have that oscillating plus-minus effect. I suppose there's equivalents in the structural mechanics area, especially with random response, say, to turbulence of airplanes, but I'm going to view that as secondary interest to us, so I hope those of you that are interested in noise in systems don't get too grumpy with me. What I will do, though, is present the stability boundaries for noise, because that is important, and we need to consider the results of that technology. And that's shown here in this Hamming rectangle, where you find that when you are below the given angled green line here, you are unstable with respect to noise. So my belief is this is the equivalent of walking up to your unstable friend sitting in the rocking chair and not just lightly touching them, but rather shaking them at some frequencies, and perhaps even through a broad frequency range of interest. And you may find that there are some frequencies in there where the person goes bananas. There really is such an instability in vision for people with some forms of epilepsy, where it can be light induced. If they have a strobe light or a flashing light at a certain frequency shined in their eyes, it can trigger an epileptic seizure. That's the kind of instability due to noise that I'm worried about here, and that can be avoided in our case by just this lower boundary that we will not pick proposed numerical integration schemes that lie below that boundary. Let me gather the information that we've just developed and put it on a single rectangle in the Hamming approach. We already know that accuracy is better when you're in the lower right-hand corner, so you'd like to go down in that direction, other things being equal. We know that stability to a small perturbation makes you lie within a certain crosshatched region, and I used red for that crosshatching, so you can see that in your notebook. Then the noise will create a bad area that will be crosshatched green, and that's the stability of the system with respect to oscillatory input. You're left with this triangular white region shown in the middle here, and then you can see a bunch of points illustrated that are given various names, and these are the various classical integration schemes that have been proposed over the last 100 or 200 years. And the one that often you hear in fluids is the Simpson rule or the Adams-Bashforth rule. Probably Adams-Bashforth is the most common. These others are given names according to the sizes of the coefficients. When I did some response of an airplane wing to turbulence, I used, for numerical integration purposes, this 1/2 rule, which I like. And I still think if I was going to pick one again, I'd probably use that same rule. It's the one that's the most accurate of the candidate rules here, and it's well in from the various stability boundaries. So that would be, you know, offhand. I don't want to give people advice because it depends on whether your system's more sensitive to noise or to various perturbations that are static perturbations, but it looks to me like the 1/2 rule would be one that you ought to consider. Well, the average viewer is saying, well, what are these silly rules, 1/2, 1/6, and so on? And here I've given you a table to illustrate these. When you look at the one called Adams-Bashforth that the fluids people are interested in, it has certain specific coefficients involved. The 7 coefficients we were talking about in the Hamming approach are these along this axis, the A zeros and through the B2. Simpson's rule is given here. Now you have a chance to look at it, and in the problem session I'll be doing a small example and showing how Simpson's rule is indeed neutrally stable with respect to a static perturbation. And then here are all the other fractional named rules. Well, we've reached a stopping point now in terms of knowing how to integrate a simple system such as a dashpot with a force on it. But really this was just indefinite integration, and we need now to progress to the integration of a true differential equation. To get a differential equation, you need to do something tantamount to adding a spring to the dashpot system. It's said in a more mathematical way here. What you're saying now is that the velocity or the derivative of the function is going to be related to not just a function of time, but a function of where the system is. And this thing called u dot, we have plotted down here. And because you don't know where the system is at the start point in time, you can't calculate the u dot either. And so both of these quantities now become unknown at the current time. You don't know what the force is because you don't know where the system is, and you don't know where the system is because you don't know what the force is. So you can see the tangle that you get into here. And that's precisely what a differential equation is. Maybe you could take a spring damper system and see if you can put it in this form. Now I'm going to suggest another nonlinear differential equation here that would do the same thing. It says that the force is going to vary like u squared plus t squared. So this would be a force that would be increasing in time, but also would increase as the system moved away from its rest position. And this force is tending to pull it further in the same direction as the, in other words, the velocity is increasing as u is increasing. This could be a very unstable system here. I think it's like a negative spring, actually. That would be a good assignment for the viewer to check out. How do you get such a first-order differential equation? And I'm suggesting that this problem here would probably have a negative spring in it, so it would be a perpetual motion machine if you could get it to work. In any event, we now have to cope with something new, namely that we do not know this quantity, and therefore we can't depend on that quantity in our general formula for finding this quantity over here on displacement. Now, you might think of our indefinite integration as a scheme for finding the function u at a time point where you already know the velocity or the derivative of the function. How can we help that method out by doing something that will give us the estimate of the current velocity, which is unknown? Well, it's called a predictor-corrector method, and we need to develop a prediction of the velocity that's missing now, that used to be known in our integration. And that's called the predictor step. Then we can use our previous information, our previous work on numerical integration as the corrector step. So we already have half the problem solved. Now, what's going to happen is we're going to have to look back farther in time in order to get enough information for a 7-parameter formula. Why? Because we're missing this current velocity. This is more error-prone to do this because you have more history behind you. We are going to call it the predictor step. And then that will provide the velocity that we're interested in that's been unknown till now, and then we put that into the corrector step. We're going to use the same number of parameters as we did before, namely the 7, and we're going to use the same in the predictor and the corrector formulas. Also, when the push comes to shove, we're going to try to keep those formulas as close as they can. I'm sure there are viewers out there who are watching this and saying, what's this guy doing to me now? I thought I understood. Here we were doing nicely integrating and tripping gaily down the primrose path, and all of a sudden he shows me that what we were doing doesn't really apply directly to differential equations. And that's right. We need to develop this predictor approach, but I didn't want to complicate things too quick for you. Now there would be two ways to do a predictor step. One would be to go back further in time and pick up a displacement, and the other would be to go back farther in time and pick up a velocity. So there are two classes of predictor formulas. Here's a Milne type predictor shown at the beginning here, and that has gone back and picked up a displacement from the time step n minus 3. The Adams-Bashforth type predictors has gone back and picked up a velocity at time step n minus 3. And of these two, it will turn out that the Adams-Bashforth is the more popular predictor. And one reason is then that the A coefficients here can be similar as they were in the corrector step, or what we had done previously. Let me repeat the corrector formula so that you'll have those different choices in front of you. Here's the displacement at time n plus 1, and rather than calling it u, we're going to call it c. And I think if you noticed on the previous formula, you would notice that I was calling the displacement p for predictor. Really, those are both displacement estimates for this quantity here. And what we're talking about is trying to predict this. Now the two cases are whether or not you know this blue star over here, which is true in the corrector stage. You pretend that you know that when that shows up right here. But on the predictor phase, that point is missing, and then you have to pick up either this round blue circle here or this one here, depending whether you're using the Milne or the Adams-Bashforth approach. And as we've mentioned, it's more common, at least in fluids, to use this point here on the velocity as the point that you go back and pick up. Let's discuss the criteria for choosing a method. Goals that we should have would involve low truncation error, large margin of stability, and protection against round-off error. Round-off means the same thing as noise, because in a computer calculation you get the twittering of the last significant figure due to round-off, and that can introduce an oscillatory effect into a computation. So this is basically what we call noise. Now, in achieving these goals for the integration of first-order differential equations, it's become common to use the Adams-Bashforth approach, because when you use it, you have the same coefficients on the displacement terms in the sampling. And that means when you compare the predicted value and the corrected value for displacement, all those terms cancel out, and you're only left with these terms below that are all on the velocity sampled terms. So pretty much Adams-Bashforth is the method you hear. When you go to fluid mechanics seminars, you hear a lot about that. The class of predictors that use an additional velocity term are called Adams-Bashforth type of predictor. I'm going to give you a table here showing a number of those predictors, including one that is specifically called the Adams-Bashforth method. These coefficients are rather intricate, as you can see, and had to be developed by the same stability and accuracy arguments that we used on the corrector. In our problem session, we'll start by looking at Simpson's rule for integration. And here we're going to look at the indefinite integration, in other words, the corrector form, in the presence of a perturbation. So we're going to look at the stability of Simpson's rule. And then, after looking at stability with respect to just a static perturbation, let's look at it with respect to some noise that moves with oscillation plus minus E and see how that jiggles the system. It's not clear how we're going to put this into the system right now. We can do that through the displacement field, but I'll show you how to do that in a second. So I've written out the equations that result from the need for accuracy, and our general integration formula here becomes Simpson's rule when you put in the remaining values for A1 and A2. Now for our stability study, we're going to do a perturbation. We'll hold the velocity 0. I won't plot that this time, and we'll show that the little chart that I like to use has an epsilon here at time step 0. And then when we carry out the succeeding time steps, we find that we get an oscillatory answer as shown over here. So the small static perturbation here has led to this dynamic oscillation. People might call this neutrally stable, and this could be acceptable in quite a few situations since it doesn't amplify. And maybe in some other situations it wouldn't be acceptable. In the second part of this problem, I wanted to look at noise, and it's a little bit argumentative how to introduce noise into this system. One way to do it would be to shake the system at that noise and then stop and see what happens. So that's what I've done. So I've continued the process for several steps here and then found what happened at the following step. And when you do that, you find that the oscillation continues. So it's not quite a good study on noise, but I think it shows that you have the same instability there that we did on the static perturbation. Let's do a practical indefinite integration with a specific dashpot and a specific load applied to it. Suppose this system's at rest at time 0, and then we use the 1/2 rule for integrating to find where it is at time increments of 1,000th of a second and 2,000th of a second later. The load is 100 newtons applied at time 0, so I use this Heaviside step function here to illustrate that the time at time 0 the load starts, and before that the load's not there. And then the damping coefficient is 10 newton seconds per millimeter. The differential equation would be this. Our initial condition would be like this. We said that this actually equals 0 at time 0, so we'll set that to be 0. And then the integral form of that is shown here, where we would again set this to be 0. We can see just from elementary physics that the velocity is going to be 10 millimeters per second, and it really should travel 1/100th of a millimeter in each time increment. Then let's just see if we get that out of our integration. Let's use the coefficients from our table to go into Hammings' general formula and get the specific integrating formula. Here's the general formula, and then here's the specific one for the 1/2 rule, putting in those constants. Then I set up the table as we've done before with 1,000th second increments, showing that the system is at rest for negative times and up to time 0. Then we find the displacement building up here as 1/100th of a millimeter and 2/100ths, and 5/100ths. Now, this is more than the classical result, so we can see that we're overestimating the displacement in this situation. Although I filled in those answers in the previous slide, here I have the actual calculations that were done, and these show how indeed the displacement after 1,000th of a second is this 0.014 millimeters, and then after 2,000ths of a second, and then I just state the displacement at the third time step. So this method is overestimating displacement by a sizable percentage. What happens though as time goes on is that generally these methods home in, and if you're getting bad answers, and I would consider this very borderline good, I mean it's sort of bad, then you have to take smaller time steps. So the viewer might look at this problem and then try this calculation over again with time steps that are much smaller, and then observe how the method converges to a better, more accurate answer. I was interested in the stability of the Adams-Bashforth corrector formula, and since it lay on the boundary of the stable region, so let's do a little check on that and check it for a static perturbation. Let's suppose we want to integrate this formula in the presence of a disturbance. That's what we've been doing before. We'll give a little epsilon disturbance. The Adams-Bashforth formula gives you certain coefficients, and here is the integrating formula. This is fairly predictable that the current displacement is the same as the past displacement under this condition. So I think this, now that's just under this condition. This isn't the general formula because we've dropped out all the velocity terms. So it looks as if it's going to be somewhat stable. So the Adams-Bashforth corrector formula isn't very exotic when you do it with the system at rest and no velocity and no force applied, and then bump it a little bit, and it just sits there, as we can easily see. When we calculate our table here, we find that the displacement at the time +1 here is the same as the past one, and same as the past one, and same as the past one. So this is just a neutrally stable method in that sense, that you keep the perturbation displacement, but it doesn't grow, nor does it die out in time. And this is probably okay. And in our integration case, it's like disturbing the dashpot from its equilibrium position, and then it just sits there. So actually, physically, this is rather understandable for our mechanical model of a first-order system. Well, that finishes our lecture on numerical integration of first-order equations, and it's meant to really be inspiration and kind of enlightening about what stability means, and then prepare us for a more serious work on second-order differential equations coming up next.